Thank you very much. So today I want to talk about the subject. So all the varieties I will consider are smooth and over C and projective. And first let me talk about the first word in the title. So what do I mean by positivity? So there are a lot of notions of positivity for vector bundles. And there are three notions that we'll care about today, which are ampleness, strict neffness, and neffness. So you take L, a line bundle. On X, as I said, smooth projective variety over X, over C. It is ample if for all Y in X subscheme, so closed subscheme, of dimension K, the intersection of L to the power K with Y is strictly positive. It is neff if for all, if you test this only on curve and you require only non-negative, so for all C curve, L times C is non-negative, and strict enough is just an intermediate condition that you test only on curves, but you require positivity. So amples implies strictly neff implies neff, and there's no reciprocal at all. And now, so this is for line bundle. Now the tangent bundle is usually not a line bundle, but a vector bundle of higher rank. So we need to say similar notions for vector bundles. So if E is a vector bundle on X, it is called star. So star, replace star by ample strictly neff or neff. If on PE, the projectivized total space of E, the line bundle, the tautological line bundle OP of 1 is star. So if E is neff, if the tautological line bundle is neff, for example. Okay. And you could say there's another reason when you have a vector bundle to cook up a line bundle, which is just to take the determinant and to say the determinant is positive, and to say the line bundle is positive if its determinant is positive. Very natural way of defining positivity. But this way to define positivity is a bit stronger, and therefore it's more interesting. So a remark, E neff implies that of E neff, and the converse doesn't hold. We'll see examples in a bit. E ample implies that of E ample, and again the converse doesn't hold, and we'll see examples in a bit. But a very surprising fact is that E strictly neff doesn't imply even that determinant of E is strictly neff. So you could have a vector bundle that's strictly neff, but that has trivial determinant, for instance. On curves of genus 2 or more, that happens. Okay, so that's the kind of positivity that we'll be concerned with today. And why do we care about positivity of the tangent bundle? Oh yes, I have many more boards I was going to erase, but no need. Perfect. So positivity of the tangent bundle or of higher exterior powers of it it originates in the following question, which is to classify varieties with minus kx positive. So varieties with minus kx ample are called Fano varieties. We know they're bonded, like there are finitely many families of them. We know their classification in dimension 1, 2, 3. So pretty nice story. And now comes a variety with minus kx neff. And they're much more numerous and much more messy. So varieties with minus kx neff, they come in 3 building blocks. So that's a result by Julian Chao and Andreas Höring that builds on several papers that I'm not going to cite entirely, but if you look at the references of this paper, you'll find your way through the literature. So varieties with minus kx neff come in 4 types of building blocks. So you have x rationally connected. That means through any 2 points in x, you get a rational curve, or a chain of rational curves, plus minus kx nef. You get the abelian varieties, so complex tori that also are projectives. You get the hyperkähler varieties, which Emanuele has been telling us about. And you get the Calabi-Yau varieties, which are k-trivial, so kx is trivial. And they're basically the last type of k-trivial varieties. They're k-trivial varieties that are neither abelian nor hyperkähler. Let's put it this way. Okay, and why is this a very sad classification in some ways? Because, okay, these, we don't even know if they're bounded, so there could be infinitely many families of them and no hope for classifying. So we don't know if they're bounded. Abelian varieties are not so bad, so let's put an OK in front of them. And rationally connected varieties minus kx nef, they're not so good, because usually when minus kx is positive, you take a multiple of it and get a morphism or a rational map to some projective space, and then you study this map. But here, you don't even know if minus kx is semi-ample, so you don't get a morphism in all cases. So minus kx may not be semi-ample. So this is, again, an obstruction to studying this type of varieties. So, well, we have this result, like this building block classification, but then studying the building blocks is not so easy. And here comes studying, so varieties with tangent nef. So varieties with tangent nef are much simpler. And the reason why is if you take x rationally connected with minus kx nef plus you ask like actually the whole tangent bundle is nef, then your variety is a Fano variety. That's a result by Demailly, Petten and Schneider. That traces back to the 90s, if I remember right. So X is Fano. And so in small dimension, you have the classification. They're much more, minus kx is ample, so it's a for sure semi-ample. So this is quite nice. Abelian varieties, well, TA is trivial. So it's automatically nef. So nothing to say about abelian varieties, but they're not so complicated, so it's fine if we have them as building blocks. And now the very nice thing is here we had this complicated hyperkähler and Calabi-Yau varieties. And now if we ask Tx nef, they just disappear, because they never have Tx nef. In fact, Tx is not even pseudo-effective. So it's very much not positive. And that's a result by Höring and Petten. That's quite recent, so 2019 for the publication year. That actually worked on refining to the singular setting. Say published this year, actually. So this is just singular. So you see, if you ask for varieties with Tx nef, it's much nicer. You get a bunch of Fano varieties. You don't know which ones, and a bunch of abelian varieties. And which Fano varieties you get, actually, there's a conjecture. So the conjecture is that if your Fano and Tx is nef, it's by Campana and Petten, and I think it's 1991. Then X is actually rational homogeneous. So what that means is that you have X is just a quotient by a Lie group. So you have a Lie group acting transitively on X. So X is very nice. You get a lot of sections to vector bundles by translating by your group action, this kind of stuff. So this is a conjecture. This is one of the big conjectures in positivity. Okay. Now I have to move two boards. Can I do it? No, not at the same time. Okay, so the philosophy of this is that if minus kx nef, we kind of know the building blocks, but they're hard to classify. And if tx nef, the building blocks are already much simpler. And now if you ask that tx is strictly nef, maybe, or ample, then you get even fewer building blocks that maybe we can classify. So now add more assumptions and classify. So theorem by Mori from the 70s is that if Tx is ample, well, you only have one possibility, you're a projective space. And a much more recent theorem by Li Wen-Yang tells you the same if Tx is merely strictly an F. So that's 2019, I think. Tx strictly an F implies X is a projective space again. So there's no difference between these two, but somehow there's a big gap between this one and Tx and F. All right. And now I want to tell you about another. So that's kind of the end of the story for the tangent bundle. And now we can look at different bundles. And the very natural bundle is to look at the determinant of the tangent bundle. So what about the determinant of Tx, which is minus Kx? Well, I already told you about minus Kx nef. I already told you about minus Kx ample. They're the Fano varieties. I didn't tell you about minus Kx strictly nef. So there's another conjecture by Campana and Petit again from the same paper. That's that if minus Kx is strictly nef, then it's just ample. So it turns out there should be no, it's just like here, there should be no gap between ample and strictly nef. Somehow you could check ampleness not just on the subschemes, but only on the curves. So this would be a very convenient criterion to check that a variety is Fano if it were true. But we don't know it yet. We know it in dimension 2 thanks to work by Maeda, and dimension 3 thanks to work by Serrano. But that's it. And so now we talk about Tx and determinant of Tx, so let's talk about the intermediate powers, like wedge 2 Tx, wedge 3 Tx, and so on. So let me state a conjecture for the intermediate powers. So take R between 1 and m of x. The conjecture is that if wedge R Tx is strictly enough, then X is Fano. And the reason for this conjecture, motivation, is that this implies that wedge R of Tx is nef, and X is rationally connected. This is a theorem by Li Wen-Yang from the same paper that I cited before. All right, so why do I make this conjecture? Why does it make sense to conjecture this? Because if wedge R Tx is strictly nef, so first of all, it's somehow a simplification of this conjecture. And second of all, if wedge R Tx is strictly nef, then X is rationally connected, so you're going to have a lot of rational curves, which is a good starting point for a Fano manifold. And this condition is going to tell you that your rational curves actually are positive when you intersect them with minus Kx. You get at least 2 all the time. And so you have a lot of rational curves which are of reasonable large degree with respect to minus Kx. So hopefully you're in a Fano manifold is the upshot of this. And this conjecture is actually proven true now. This conjecture is for R between 1 and m of x, yes. And for I equals dim of x, you exactly recover this one. Okay, so let me now state the results of this talk. So first of all, there's another result by Li Wen-Yang that does a cage of wedge 2. So what they do is actually, so same paper. If wedge 2 is strictly nef, then of course you have the projective space again. Or you could be a quadric, like a hyperquadric. And you can check the hyperquadric has wedge 2Tx actually ample. Okay, so projective space are, okay, maybe I'll put it as an index because it's not a product. Okay, and now I want to say the theorem for 3, 4, and dimension -1. Dimension -1 is interesting because somehow it should be the most general case after minus kx. So if you prove that it's true for n-1, then it should be true for the other r's as well. So I'll set the results and then we'll prove some particular cases in them. And the upshot is really that if you have some positivity of the tangent bundle and then a lot of rational curves, you can somehow deform them and do a lot of things with that. Okay. Okay, so r equals 3. The theorem is that it works. X is going to be Fano. And moreover, okay, we don't have a full classification, but we have two possibilities. Either x is p2 times p2, so just one 4-dimensional example, or x has pk number 1. And this example is hard to classify. And I know, for instance, the cubics will satisfy this, and also the complete intersection of two quadrics. But I don't know about maybe other del pezzo manifolds satisfy this. I'm not sure. So this case is still very much open. This case is settled. Sorry, and if there's also an assumption that the dimension of x is at least 4. Because if x has dimension 3, then this condition is just that minus kx is strictly enough. And so it's much weaker, and you can't conclude as much from it. You can just conclude that x is Fano manifold, and then you have 100 and something possibilities. And so same theorem for wedge 4. So if wedge 4 tx is strictly enough, and dim of x is at least 5 now, so that, again, we don't get minus kx here, then x is Fano. And x, so there's now a list of 5 possibilities, sorry. P2 times P3, P2 times a quadric of dimension 3, P3 times P3. So this one are not so surprising because they stem from the varieties that have Tx ample, or T of wedge 2 Tx ample. So not so surprising. And then you get the blow up at a line of P5 and the projectivize of a tangent space of P3. So 5-dimensional examples. So these are more surprising, and all of these actually satisfy, if you compute wedge 4 Tx, that it's actually ample. So actually a bit stronger. Or again, rho x equals 1, and here I expect that there is a bunch of examples with rho x equals 1 that I have no idea how to classify. Okay, maybe a word of why we had this assumption of pk number 1 is because the proof works with Mori theory, like looking at Mori contractions of x. So if x has a pk number at least 2, it's going to have at least one Mori contraction, and you can look at what the contraction looks like. But if rho x equals 1, well, the Mori contractions are just contracting to a point, so you can't say much about them. So that's the reason why we have this 2 cases. And now let's come to the last theorem that has nothing to do with Mori contractions, so it's a bit more general. So if wedge dim x minus 1 of tx is nef, and x is rationally connected, well, you could also assume this one's strictly nef, but this is more general somehow. then X is Fano. And this, I'm going to explain the proof in a second. I just want to give a remark that when I proved these two theorems, I didn't know if X was going to be Fano or not, and it really followed from the classification that is Fano. So I proved the classification, and then as a consequence, X was Fano. But since then, I gave a talk about exactly this at Tokyo this summer, and Watanabe, who works on the similar thing, was in the audience, and he figured out the proof of the conjecture up here, using this result. So he uses this result, and then he uses somehow that dim x minus 1 is the least constraint. And so that if you have this result, then you should have it for all R as well. Proves conjecture, I didn't give it a name, conjecture, let's give it brackets and recall it. So the conjecture that if you're Neff and rationally connected, then X is Fano. So that kind of settles it. You could still classify, but at least you know you're going to wind up with Fano things. Nice. Are there questions so far? No? Good. Then I'm going to switch the bars again, and we're going to come down to prove this result. And in this case, discuss why we only have one case in dimension 4. I won't prove it's P2 times P2, but I'll start the proof somehow. And if you're interested, you can read the paper and read maybe one more page, that one I explained to you, and then you'll know everything. All right. So while I erase the board, I can tell you the main secret for proving this theorem, and you can think about it. The main secret is this Hirzeberd-Riemann-Roch formula. And let me erase the board. All right, so what about chi of x of x? So we're in the case, in this case. Okay, let's start with something else at chi of x of x. An x rationally connected. What we can say is, what we can first prove is what I told you about, that on rational curve minus kx is positive. So take a rational curve, actually it's normalization. Then its intersection with minus kx is at least 2. Well, the proof is not complicated. You pull back the tangent bundle to P1, then it's P1, so it splits. So it's OP1 of A1. It has rank n, so it goes until OP1 of AN. And we order those in an increasing order. And now what we say is if you do f pullback of wedge n minus 1 of tx, this is supposed to be Neff. So the coefficients in this one are supposed to be non-negative. And what's the first coefficient? It's going to be a1 plus a2, etc., plus an minus 1, because you have n minus 1 here. Neff. So a1 plus an minus 1 is non-negative. And now what about an? Well, you have a map from TP1 to f pullback of tx, because f is from P1. And this map is supposed to be non-zero, which means an is at least 2. So if you sum up all your coefficients, you get at least 2, and that's why this number is at least 2. You could basically see the trick that if here you were asking strictly F, you would have at least 3, because you would have this is at least 1. And you could do the same with wedge 3, and let's write it really quick. If wedge 3 is strictly F, then minus kx times fp1 is going to be at least n minus 1 by exactly the same result. So let's keep this in mind for later on. And let's come back to this setup. So we now know what's going on in rational curves. And now the very nice thing is imagining minus kx. So minus kx is a determinant of this, so it's nef. Imagine it's also big. If it's nef and big, it's semi-ample, so you get a morphism. Let me write it down. Lemma, if this is nef and minus kx is big, then x is Fano. And the proof is that minus kx is semi-ample, so you get a map from x to a certain w with dim of w equals dim x. This is just a birational map. And now this map, by a result of Kawamata, is going to have to contract some rational curves. But this map contracts exactly the k-trivial curves. So it's going to contract, there's going to be a rational curve that's also k-trivial. But we just said on rational curves, the number is always at least 2, so it cannot be 0. So this is not possible. So this cannot contract any curve, so it's a finite morphism, which means that kx is ample. Minus kx, sorry, is ample. So contracts no curve. All right, so the hard work is going to be to prove that minus kx is big. Or another way to say it is that minus kx, when you intersect it with itself n times, where n is the dimension, you get something non-zero. So this is the big question for now on. Okay. And now comes the Hertzebel-Riemann-Roch formula. So x is rationally connected. So if you look at chi of x ox, it's 1. Why? Because x is rationally connected, so you don't have... OK, I have to think about the blackboards for a second. I think it's this one. Yes. OK, so x is rationally connected, so chi of x ox is 1. But now chi of x ox is also a polynomial in the Chern classes by the Hertzebel-Riemann-Roch formula. It's a complicated polynomial involving Todd classes, but we only need to know that it's a polynomial, and we don't need to know which polynomial it is. And now the thing is, OK, I need to write. OK. We're going to prove that it's OK. So chi of x ox is 1. And it's also a polynomial on C1 of x until Cn of x, which are, so in my notation, Ci of x is Ci of omega 1 of x, of the cotangent sheaf. What I want to tell you is that this is also a polynomial, and C1 and the Chern classes of this bundle. Why is it a polynomial in these? Because each of these is going to be a polynomial in these. And the reason for that is that n minus 1 tx is just omega 1 x tensor minus kx. So the Chern classes of this you can express from the Chern classes of this and the Chern class of this, which is just this one. So this formula implies that Ci of wedge n minus 1 tx is a polynomial in C1 of x until Ci of x. So now P tilde is just a composition of P with all of these small polynomials. So there's this big polynomial that pops out, that gives you away the other characteristic of OX. Sorry, okay. Yes, that's good, but now this one is an F. And there are inequalities for the chain classes of Neff bundles. They're given by Demailly, Pétain, and Schneider. And maybe the one you know is that C1 squared is always bigger than C2 for a Neff vector bundle. And that generalizes. So okay, I wrote their names already, so let's go by DPS. So C1 of x to the n is going to be bigger than Cn of x, which is going to be positive. Non-negative, sorry. And Cxn, you can do the same with C1x, Cn minus 1x, like this. And actually, you can do the same with every monomial of degree n. So with powers as well. So if the sum of the alpha j, ij equals n. So those are very general inequalities. And now we want to prove that this is big. So that this top intersection is non-zero. But imagine it's 0. That means the first chain class is always 0. So all the monomials in the chain classes are 0. So all the polynomials in the chain classes are also 0. So this polynomial should be 0. But it's 1, so it's not possible. So equals 0 f minus kx n, which is C1x n is 0. Contradiction, because 0 is not 1. So the only possibility is that this number is strictly positive, to allow all these monomials to be positive, to allow for this polynomial to actually be 1 and not 0. That's it. So that's a proof of the theorem up there. No, the theorem just on the middle board. Okay, so that was the chain class part, and now let's move on to Mori contractions and do a little bit more of birational geometry. I have 5 minutes left. Perfect. Okay, if I spend 5 minutes moving the boards, that's not going to be great. Okay, this was a proof. I'm not going to use it anymore, so I'm just going to erase it. The sideboards, yes, that's a good idea, sorry. Okay, next time. So I'm just going to explain you, okay. So now we're in the setup in which 3 of Tx is strictly enough. And we want to prove that x is Fano. So wedge is strictly enough, and we assume that the Picard number is at least 2, so that we have at least one Mori contraction that we can work with. And I think the only thing that I'm going to prove you is that if x to w, call it f, is a Mori contraction, so a contraction of a negative, of a kx negative extremal curve, then f is divisorial or of fiber type, or fibered. So you might know that there are 3 types of Mori contractions. Basically, they are the one that give you a fibration, then the one that send x to a w of the same dimension but contract some divisors, just like a blow-up, like the opposite of a blow-up. And then there are very bad ones that contract some curves only. And then the w gets to be very singular. And what I'm going to prove to you is that the bad ones, which are called small contractions, don't happen. prove that f is not small. Yeah, if E in X is a component of the exceptional locus, dim of E is at least n minus 1. So either the exceptional locus is everything, so fibered, or the exceptional locus is a divisor, so n minus 1, but not n minus 2 is a thing, or not smaller. Well, Robert talked about it in his talk. We're going to use Ionesco-Vishnevsky inequality. So it's two different papers, but let's put their names together. I don't remember the year, unfortunately. So what it tells you is that dim of such a component E plus dim of F, where F is a general fiber of our Mori contraction restricted to the general divisor, is at least dim of X plus minus kx times C minus 1, where C is a primitive class in the whole array of the Moricons that's contracted, in the array contracted. So C is just one of the contracted curves, and you know, if C is contracted, then the curves that are numerically equivalent to 2C are also contracted, but we take not 2C, we take the C, the first one. Okay, and by our result that I highlighted up there, this is at least n minus 1, this is n, so this is at least 2n minus 2. And now we said, imagine this is, so this is at least 2n minus 2, this is at most dim of E. So so this is at most 2 dim of E. So divide by 2 on both sides, you get that dim of E is at least n minus 1. And that's why you only get small contractions. And how much time? Do I have time left or no? Okay, perfect. Thank you very much. So we ruled out the small contractions. We can rule out the divisorial contractions because basically proving that all the divisorial contractions are like blow-ups of one point. And then looking at if you have the blow-up at one point, you know the kx downstairs, the kx upstairs, they relate like by adding some exceptional divisor. And you look at this formula and you rule out using the minus kx times c is at least n minus 1 again. And then the hard case is when you have a fibered Mori contraction. And what you want to prove is that this fibered Mori contraction is actually equidimensional, and then that proves that it's a P2 bundle. And then to prove that the P2 bundle is actually trivial, so it's P2 times, and the base is P2, so it's just P2 times P2, like a trivial bundle of P2. And the hard part is to prove that it's equidimensional. And for that, you have this Mori contraction and you just build another one that's somehow orthogonal. It's a strategy. And when you have your two Mori contractions, you say that if you have a big fiber and one Mori contraction, then it's going to be sent to the base of the other, and so you get some contradiction by looking at dimensions. So that's the philosophy. And the case with wedge 4 is actually much more technical, because in this case you could have a divisorial contraction. The blow-up of a line P5 has a divisorial contraction. And that's it.
So in the remark of Watanabe,
yes.
we suppose that R is smaller than dimensional X? Or?
Yeah, strictly smaller, exactly. Yes, thank you very much. So R is between 1 and dimension of X.
You didn't mention ampleness. I mean, if some exterior power of the tangent bundle is ample, are there results?
No. So, well, there was for Tx and for wedge 2 Tx, but for wedge 3 and wedge 4 it's new. And what I proved is actually that if it's strict enough, then in the Picard at least 2 case, all the examples actually have ample. So we strongly conjecture that if wedge R Tx is strict enough, then it's also ample. But in the case rho equals 1, you still have something to prove. To use
Because
what?
I see you use the fullback of the function.
Yes, yeah.
So, and the curve is 3, A1 is.
So the manifolds are rationally connected, so they're uniruled, so you're going to have like curves that are free, and I think indeed very free. And actually, what you mentioned is actually the strategy for studying the fibered contraction is you take like free curves or very free curves, and then you look at how they deform, like if the family is unsplit, if you know what that means, and what the locus of the family is, and then you fix a point, and you look at the family with the point fixed, and you look at the locus of this. So that's exactly the strategy.
Can you do this for like mapping singular people?
Not even, I don't even know if Tx is ample, if X turns out, and X is singular, if X turns out to be the projective space or not. So it's entirely different, I guess.